So this is a sample problem. You may hear a little background noise because I'm in a tire shop. There you go. But we're going to do a gas stoichiometry problem as an example. We have phosphoric acid. That'd be H3PO4. Phosphoric, of course, phosphate becomes phosphoric means phosphate because of adic-itis. ATE ending means the IC acid ending. Okay, we can combine that with sodium carbonate, which is so that we're going to make sodium phosphate. It's a double replacement reaction, so sodium phosphate has to be Na3PO4 because of the +1 -3. Plus the other product would be H2CO3. Carbonate's -2 and hydrogen's +1. But you remember that carbonic acid always decomposes into water and carbon dioxide. Alright, so to balance the equation, we're going to need to put a 2 here and a 3 here. That would give us 2 PO4s. We put a 2 there. So put a 2 in front of the sodium phosphate. That gives us 6 atoms of sodium, so we need to put a 3 over here. And there's our balanced chemical equation, it looks like. Oh, wait a minute. Did I put a 3 in front of the water over here in front of the carbon dioxide? There we go. Now it's a balanced chemical equation. We're given 200 grams of phosphoric acid, and 250 grams of the sodium carbonate.
What's up, man?
I'm going to assume that you know how to change the moles. So the 200 grams of phosphoric acid, divide that by 98, which is a formula mass, so that gives you 2.04 moles of that.
What's that last input?
And then the sodium carbonate, you got 250. You're going to divide that by 106, and you're going to get 2.35 moles of sodium carbonate. So we're looking at a 2 to 3 ratio. I need, if I take the 2.04 moles of phosphoric acid, then determine real quick how many moles of sodium carbonate I would need to consume that to be a 3 to 2 ratio. So I'd end up with, 3.06 moles of sodium carbonate. That's how much I need. But I don't have that much. I only have 2.35 moles. So that means that the sodium carbonate's limiting. It's going to run out first. So the amount of product is going to depend on the sodium carbonate, which I'm going to write here. And the question asked about the gas, what volume of gas you could collect. So what we're going to need to do is find the moles of carbon dioxide. So we're going to have sodium carbonate on the bottom, and we'd have carbon dioxide on the top, and that's a 3 to 3 ratio. So it just turns out we'd have 2.35 moles of sodium carbonate. Oh, excuse me, moles of carbon dioxide, I meant to say, carbon dioxide. Alright, so now we got 2 ways we can go. We can go 22.4 liters per mole. That would give us some number of liters of gas, but that would be at STP. Then you'd have to set up a T1, T2 problem. I'm not going to go ahead and work this all out, but remember that T1 would be 273. T2 would be 298. No, is it 298? Yes, 298 because it was 25C. These are both Kelvin temperatures. Alright, so you get the idea that you set up a P1, P2, and so on. Well, actually, let's just go ahead and do it. So P1 would be, pressure here is in kilopascals, so P1 would be 101.3. P2 would be 103 minus 3.2. Alright, now the reason you're taking away the 3.2 is because it's collected over water. So you have to subtract water vapor pressure, and I happen to remember off the top of my head that water vapor pressure at 25 degrees C's is 3.2 kilopascals. Alright, V1 would be whatever the answer was up here. and V2 would be your final answer. All right, so I'm not going to actually work through it, but that's how you would do it. I'm going to use PV equals nRT, which is easier. Simpler, I should say, maybe not easier. So PV equals nRT. The pressure we would use would be 103 minus 3.2. Now once again, let me tell you why that is. You have to look on your water vapor pressure table. The temperature is 25 degrees Celsius. The pressure table that I gave you is in millimeters of mercury. So you would look up what it is in millimeters of mercury. Let me put this little box right up here. So you'd have millimeters of mercury, like this, times. You're going to have millimeters of mercury on the bottom. And then you got kilopascals on top. 101.3 is standard pressure, and 760 is standard pressure. So those are equivalent to each other. So whatever this number is on your table right here, you'd multiply by 101.3 and divide by 760. Alright, so that's how you make the conversion. It turns out to be 3.2. Volume you don't know, so just put a V in. Moles you know is 2.35. Alright, R for kilopascals, the value on your table is 8.31 liter kilopascals per mole Kelvin. Now I gave you a little reference sheet that had all kinds of gas law information on it. That reference sheet tells you this value of R. And the temperature would be 298 because it's 25 C, so you put 298 in. Then you solve for volume. So I'll go ahead and do that real quick.
If you decide to go with them, I can order them today and have them in here Monday morning.
Come back, after 3 o'clock. Because my wife drives.
On Monday?
Yes.
Yeah. So yeah, I mean, just if you decide to go with them, shoot me a call today, and I'll have them here. We can get them on for you Monday. Yeah, and they get.
That came out to be 99.8 for the pressure, just FYI. So my final volume is 58.3 is what I got on my calculator, and I'm doing here on the side. So 58.3
Yeah, if you decide, just shoot me a call.
Okay.
All right?
Okay, thank you.
No problem.
liters. And that's your final answer, 58.3 liters. All right, so that's how you're doing. So quick review, write the chemical equation, determine which reactant is limiting. After you know the reactant that runs out first, you find the moles of gas. After you find the moles of gas, you can use PV equals nRT to find its volume.